Okay. Okay, so good morning, everyone. How is FYP treating you so far? Students, I need to hear your voices. Are you tired already? Nope. Fresh start again today?
They're sleeping.
Still sleepy. So how many more days before FYP is over? Anyone?
In chat room, dude.
Unmute la. Wait.
Until this week, right?
Okay, 1 week, end of this week, 2 more days. Okay, this Friday, including today. Okay, nice. So it's almost done then. You'll be ready for class starting next week already, and hopefully you're not totally burned out by then. All right. So this is actually our school-specific session, and our topic for discussion for today is actually pretty much the foundation of what? Computer science. Okay? So I'll be with you. We will be with you for the next 100 minutes or less. And then we'll actually be seeing each other again tomorrow. But this time, we wouldn't be the one presenting. Not me, not Bagus, not Paray Magbahana, not Nurul, but it's going to be your turn presenting. Okay. Okay. So with that, I guess I'd like you to watch a video first. Okay. Just to see how computer science is actually affecting the world we're living in right now. Okay?
The 19th century was about the Industrial Revolution, about electricity, about disrupting the agricultural society and making it more advanced. The 20th century was about physics and engineering, to do more things easier in our everyday life, from refrigerators to washing machines. And the 21st century is definitely the digital age. It's the internet.
Even if you want to become a race car driver or play baseball, or build a house, all of these things have been turned upside down by software.
The lettuce bot is a robot that can sense its environment. Every single hour, this lettuce bot is seeing 1.5 million plants, and it's taking individual action on those. We enable lettuce growers to have higher yields in their fields, by helping make it cheaper, by helping produce food in a more sustainable way. And that wasn't previously possible without computer science and technology.
I have a really fun job where we build Polymore, which kind of combines all my favorite things, so programming as well as fashion, art, and design, and shopping. Half the products we use these days are software products that you play with on your phone. And so if you want to build something cool, you need to know programming, right? And there's so many things that you can do with computer science. So if you just work backwards to the cool thing that you want to build and figure out what that is, a lot of times computer programming is part of that, right? So you should learn this skill.
It's really exciting right now. The technology that we're developing right now is going to be used by your doctor in the next decade. When you come into the office and you're sick, and the doctor is going to be like, all right, spit in this cup. And I will put it into this magic machine, which is a sequencer. And in an hour, I can tell you what you have or what's wrong with you. So if we're looking for a new virus, for example, we'll download a database of all the viruses that are known. And we'll search for, our sequence of interest against a whole database of all viruses. So you still need somebody to analyze the data. The computer is not smart enough yet.
Our software helps people save energy and thereby reduce their carbon emissions. To date, we've saved over 8 terawatt hours, which is the equivalent of about 1.1 million cars on
when you're forecasting and when there's so many different parameters that go into it, it would be impossible for a human to sit down and do all those calculations. We need a computer model in order to forecast it.
I write software which scans images. Looking for bad images that were not needed. I work very closely with organizations like the National Center for Missing Children. I know that the work that we've done has impacted the life of people. And I feel very strongly about it because there's a lot of social problems right now that could really manage because of technology. It's a lot about empowering people who are there helping the world by giving them tools to be able to do better. That's something that we can do right now, and the tools available are free.
The merging of art and technology is getting more and more significant now because computers and software are such an integral part of our lives day to day. People are realizing that it can be quite creative to take this medium of computers and create incredible works of art.
And finally, you know, when Crush and Squirt and all the friends are flying through the East Australian Current, you're seeing images of water flowing by, you're seeing the colors on the back of the turtle, you're seeing the sides of the fish. All of those things are generated through math and computer programs that we write, that we then give to the artists, and they take that to create that final image and tweak it and make it look beautiful and look fun.
The crux of it is really about invention. It's about looking at the world and being dissatisfied with things and questioning everything.
I always felt like if I didn't learn how to program, it would be like not learning how to read. You know, the future would just be closed to me.
If you're in the coding profession, there's so many things that you can do, and you can pretty much pick and choose the course you want to be in.
I think that you can start something in your college dorm room, and you can have a set of people who haven't built a big company before come together and build something that 1 billion people use as part of their daily lives is just crazy to think about, right? It's humbling and it's amazing.
Really, it's about the chance to reinvent things and then see it out there in the world and see people using it and having fun or having a better life because of something that wasn't there before that you put in the world.
Okay, so with that, what could you conclude from the video? Anyone? Feel free to speak up. Come on, guys. We picked the right major. Right, cool. I mean, given the time that we're in right now, it's a perfect opportunity to be in this field of into this field, right? So hopefully we would be able to be catalysts. We would be able to change the world by the aid of a computer, right? So, yep, pretty cool. Okay, so as I've mentioned a while back, we are gonna talk about the basics, okay? Before we actually try to learn programming, we actually need to learn the foundation, which is actually algorithms, okay? So by learning how an algorithm works and what it is, we would be able to implement those into an actual program, and of course we'd be able to do whatever we please as long as it's possible, okay? So let's say, for example, oops, okay, I am an artist, okay? So if I was an artist, what are the tools that I need to create art? Definitely, I'd be using my pen. I'd be needing a canvas, right? So I express my feelings and emotions into my line of work, and I'd be able to create something. Got it? That is if you were an artist. If you were a musician, then most likely you'd like to hear your thoughts be heard by actually creating music. And the tool that you use is definitely what? Sheet of paper, perhaps. You learn how to write notes and write notes. And you use your specific what? Tool, like a guitar or a piano, to express what you'd like to create. right? You're a musician, for example, or DJ, those things and stuff. So basically, the tools that we actually use are a medium for problem solving and self-expression. Okay, so in the field of computer science, what is the tool that we use to solve problems and express ourselves? Definitely, we actually use what? A computer to solve the problems. Got it? But with that, we actually need what? The underlying knowledge so that we would be able to have an impact in everyone's life. Okay? Because as what was stated in the video a while back, right? Computer science is changing everything, right? From different fields, agriculture, medicine, you name it. Once you graduate, or not even if you're not yet graduates, for example, but if you are skilled enough, then you would be able to make a change and impact already. Okay? So what does it take to be a computer scientist? So at least you should have a strong grasp of mathematics and computer systems. Okay? As you've seen a while back, right? Let's say, for example, the animation effects that was used in Finding Nemo, for example. And they actually showed you like a programming language, which is very, familiar. It's the first programming language that you'll be learning starting next week. It's Python. It's gonna be delivered by me and Bagus. Okay, so you should have a strong grasp of mathematics and of course computer systems as well. On the other hand, you should also be creative. Okay, you should be inquisitive, as what they said, right? Don't feel afraid to ask questions. The best way to learn is to ask questions. Verify your thoughts. Don't just assume everything. And do not believe everything that your lecturer says. You have to question everything. Okay? Got it? You have to be analytical and very detail-oriented. However, you should be able to work in a team and you should be able to communicate your thoughts as well. Okay? So everything should be balanced. It's like the yin and the yang, right? Got it? Your soft skills and your hard skills or technical skills working together. Okay? So, this is actually the road, your first step to being a computer scientist. So, what does it take, right? So, starting out, you have to become a lifelong learner. Okay? Learning doesn't stop. Until now, we're still learning. Okay? You just don't be content on like, hey, okay, I know this already and I'm done. Okay, in our field, it's very dynamic. And so we have to be lifelong learners. We have to know and understand our role in the future. And what is our role? We're problem solvers. Okay? So how do we start off? Definitely, as I mentioned, yeah, you start with like writing pseudocodes. Okay, pseudocodes are algorithms. Okay, you start with it, then you tweak it. Okay, if I say you start writing pseudocode and then you tweak your pseudocode, it's actually saying that the first solution is not always the best solution. Okay, people come up with better solutions each and every time. Even you, maybe in your first semester you solve a specific problem, and then in your third semester you encounter the similar problem. However, you actually do it in a more efficient way. Okay? So when writing algorithms as well, yeah, you have to try writing algorithms for all sorts of things. Not just the problems that are being given to you by your lecturers or a homework, for example, but even in your daily lives. Okay? So after you've learned them, then you would be able to, what? Programming should just come in naturally. Okay? Algorithms are just what? Steps, a sequence of steps, a sequence of finite steps that you do to solve a problem. So without even thinking of a programming language, you should be able to write algorithms. Okay? So as mentioned here, right, programming is only a translation of pseudocode into a programming language. So all the algorithms that you write, regardless of how you write it, in your native language, whatever, you could be able to implement it into any programming language. Okay. In addition, you should also be able to learn how to analyze it, so that you would be able to come up with more efficient algorithms in the future. Okay. Now, question: could anyone tell me what this conveys? It's actually conveying some sort of an information. Okay. So anyone could share what the information is being conveyed here, regardless if you know how to program or not. Try understanding it. I'll give you like, what, 2 minutes to look into the code and see what information is actually being conveyed. The first one to get it gets a bonus. Okay. Think it's a game. Character creation, game character. Okay. But in general, setting the difficulty, okay, game character. It's a song. Hey, this one's quite cool. Looks like the start of a game, so it's a new game, right? Cool. Okay, so everyone thinks it's a game. You really are gamers, are you? Music, okay. Rafi, what made you think it was music? Turn on your audio and please sing the song for us if you know. There's a difficult.
I don't know this song, but in the end, there's a play piano here.
Okay. So anime, right? Okay, there's piano that play. Cool. So notice that, hey, even if you're actually don't know how to program, you could be able to look into some code and also what? Deduce what type of information is actually being conveyed. Also possible, right? Okay, so sympathy that clears for me. Okay, so let me give you a clue. Yay, Morris. Okay, someone said it's Bohemian Rhapsody. Do you agree? Okay, so this one, let's try and catch this, yeah. So you're actually asking, is it a real life or it's just a fantasy, right? Got it? Got it? Then you're caught in a landslide. No escape from reality because this is a loop and it's actually an endless loop. Open your eyes, look up to the sky and see, right? I'm just a poor boy, my wealth is no, right? I have no sympathies because I'm easy come, easy go, little high, little low, anywhere the wind blows, right? Doesn't really matter to me. And then the piano plays. Cool, right? All right. So that's one thing that you actually could be able to create. Computer science students are too antisocial to know. Nah, we're all computer science students here. And are we antisocial? It's good being antisocial, you know. Big brain. Okay, now your big brains are working. Right, so let's keep moving. So these are the programming essentials that we actually have to look into, okay? First, we have to understand the task that the program is to perform. Okay, so if you're given a problem, do not code immediately. Got it? Coding is the last step you need to think of. Okay, you have to find out, okay, if you're given a problem, you have to know what is the input and what are the outputs. Once you know what the input is and what the output is, then you come up with a process or an algorithm on how to be able to solve it. Okay? You could use flowcharts or pseudocodes to convey the thoughts that you know, right? So let's say, for example, you're given a task. Write a program or an algorithm to compute for the volume of the sphere, for example. So what is the very first thing that you need to think of? First is what? You have to know the formula. Perfect. Right, Darren? Okay. Once you know the formula, you would now be able to identify what are the inputs. Got it? Because the output you already know. The output is the volume of the sphere, right? Okay. Now you have to know what the formula is. It's like what? Volume of the sphere is computed as, okay, 4/3 pi r cubed. Very good. You're the Googlers, right? Or you actually know this by heart? Okay, now you have it. What are the inputs? Okay, what are the inputs? Nice, cool. Okay, so the inputs are the radius and pi. Pi is actually a constant, right? So you could actually be able to substitute the values of the radius and pi into the formula, and then you'd be able to get what? And compute for the volume of the sphere. Thereafter, you just print the output. Nice, pretty smart, cool. Okay, I'm starting to love this batch. Gus, you're loving this batch?
Yeah, absolutely.
All right, so moving on, let me just try playing some videos of how we actually would be able to define what an algorithm is. Oh, what's this? I love my teacher. Puts anime in his slides. Where? Look at his avatar. Okay. Okay, let's try playing a video and see what an algorithm is. Oops, sorry, not that one first. Let's play this one. Can I make it bigger? No.
What's an algorithm? In computer science, an algorithm is a set of instructions for solving some problem, step by step. Typically, algorithms are executed by computers, but we humans have algorithms as well. For instance, how would you go about counting the number of people in a room? Well, if you're like me, you probably point at each person, one at a time, and count up from 0. 1, 2, 3, 4, and so forth. Well, that's an algorithm. In fact, let's try to express it a bit more formally in pseudocode, English-like syntax that resembles a programming language. Let n equal 0. For each person in room, set n equal to n plus 1. How to interpret this pseudocode? Well, line 1 declares, so to speak, a variable called n and initializes its value to 0. This just means that at the beginning of our algorithm, the thing with which we're counting has a value of 0. After all, before we start counting, we haven't counted anything yet. Calling this variable n is just a convention. I could have called it most anything. Now, line 2 demarks the start of a loop, a sequence of steps that will repeat some number of times. So in our example, the step we're taking is counting people in the room. Beneath line 2 is line 3, which describes exactly how we'll go about counting. The indentation implies that it's line 3 that will repeat. So what the pseudocode is saying is that after starting at 0, for each person in the room, we'll increase n by 1. Now, is this algorithm correct? Well, let's bang on it a bit. Does it work if there are 2 people in the room? Let's see. In line 1, we initialize n to 0. For each of these 2 people, we then increment n by 1. So on the first trip through the loop, we update n from 0 to 1. On the second trip through that same loop, we update n from 1 to 2. And so by this algorithm's end, n is 2, which indeed matches the number of people in the room. So far, so good. How about a corner case, though? Suppose that there are 0 people in the room, besides me, who's doing the counting. In line 1, we again initialize n to 0. This time, though, line 3 doesn't execute at all, since there isn't a person in the room, and so n remains 0, which indeed matches the number of people in the room. Pretty simple, right? But counting people one at a time is pretty inefficient too, no? Surely we can do better. Why not count 2 people at a time? Instead of counting 1, 2, 3, 4, 5, 6, 7, 8, and so forth, why not count 2, 4, 6, 8, and so on? It even sounds faster, and it surely is. Let's express this optimization in pseudocode. Let n equal 0 for each pair of people in the room. Set n equal to n plus 2. Pretty simple change, right? Rather than count people one at a time, we instead count them 2 at a time. This algorithm is just twice as fast as the last. But is it correct? Let's see. Does it work if there are 2 people in the room? In line 1, we initialize n to 0. For that one pair of people, we then increment n by 2. And so by this algorithm's end, n is 2, which indeed matches the number of people in the room. Suppose next that there are 0 people in the room. In line 1, we initialize n to 0. As before, line 3 doesn't execute at all since there aren't any pairs of people in the room. And so n remains 0, which indeed matches the number of people in the room. But what if there are 3 people in the room? How does this algorithm fail? Let's see. In line 1, we initialize n to 0. For a pair of those people, we then increment n by 2. But then what? There isn't another full pair of people in the room, so line 2 no longer applies. And so by this algorithm's end, n is still 2, which isn't correct. Indeed, this algorithm is said to be buggy because it has a mistake. Let's redress with some new pseudocode. Let n equal 0. For each pair of people in the room, set n equal to n plus 2. If one person remains unpaired, set n equal to n plus 1. To solve this particular problem, we've introduced in line 4 a condition, otherwise known as a branch, that only executes if there's one person we could not pair with another. And so now, whether there's 1 or 3 or...
Okay, so it seems there's a problem with the audio, right? Could just share the, yeah, maybe later, not too bad, okay. Okay then. So can we continue playing it? All right, okay, thanks. But yeah, before I continue playing it, I'd like to ask, is the concept of an algorithm clear? Right? So you could be able to see and define that an algorithm is a finite set of instructions, got it? Which accomplishes a certain task. Now, pseudocode is actually what we call quasi-English, wherein we would be able to write an algorithm in terms of what? The syntax or semantics of a certain programming language already. It's very near to a type of programming language, okay? So what English again? Quasi. Okay, we call it quasi-English, right? So that's how I call it actually, okay? So you would be able to see here as well that this, as I mentioned a while back, right? The first solution is not always the best solution. So it actually shows us that our algorithm works first, and then we try to optimize it, and then we try to improve it to make it more efficient. Okay, it's just stating that, okay, you could come up with the first solution, it's working, however, there's always room for improvement, right? Okay, now let me try playing the other video. Okay, but if, just mention if the audio is not as audible, then we could just move on to the next slides. We'll be sharing you the link to the presentation so that you would be able to watch it at the comfort of your own homes later. Okay?
Mission might be a set of steps to accomplish a task. You might have an algorithm for getting from home to school, for making a grilled cheese sandwich, or for finding what you're looking for in the grocery store. In computer science, an algorithm is a set of steps for a computer program to accomplish a task. Algorithms put the science in computer science, and finding good algorithms and knowing when to apply them will allow you to write interesting and important programs. Let's talk about a few famous algorithms. How does Google Hangouts transmit live video across the internet so quickly? They use audio and video compression algorithms. How does Google Maps figure out how to get from Dallas, Texas to Orlando, Florida so that you can get to Disney World. They use a route finding algorithm. How does Pixar color a 3D model of a character based on the lighting in a virtual room? They use a rendering algorithm. How does NASA choose how to arrange the solar panels on the International Space Station and when to rearrange them? They use an optimization and a scheduling algorithm. Those algorithms are more complex than our everyday algorithms, like making a grilled cheese sandwich, but they boil down to the same thing, a set of steps to accomplish a task. If you know something about existing algorithms, you can save yourself some effort and make your programs faster by applying the right one. For example, let's say that you're writing a game and you want the user to be able to play against the computer. Well, you could look at checkers games for inspiration. Computer scientists have figured out how to write checkers programs that never lose by using the minimax search algorithm to search through the huge tree of possible moves. If your game is similar to checkers, then you might be able to use algorithms based on these techniques. If not, then knowing the limitations of those algorithms might lead you to redesign your game if it requires having a skilled computer player. It's also important to know how to design new algorithms, as well as how to analyze their correctness and efficiency. In the biological sciences, new algorithms are continually being designed for purposes like designing the molecular structures that are the core of disease-fighting drugs. In physics, algorithms simulate climate and weather patterns, and other algorithms search and analyze the vast data about stars in the universe that's collected by automated space telescopes. Across all the sciences, and even on websites like Khan Academy, efficient algorithms are needed to analyze huge data sets or to select intelligently from a vast number of possible decisions. In just about any area you might be interested, new algorithms will allow massive computational power to be harnessed to do things that people really need and care about. Now, not all algorithms are created equal. So what makes a good algorithm? The two most important criteria are that it solves a problem and that it does so efficiently. Most of the time, we want an algorithm to give us an answer that we know is always correct. Sometimes we can live with an algorithm that doesn't give us a correct answer or the best answer because the only perfect algorithms that we know for those problems take a really, really long time. For example, let's say we want a program that would determine the most efficient route for a truck that delivers packages, starting and ending the day at a depot. It would take weeks to run, going through all the possibilities. But if we're okay with a program that would determine a route that's good, but maybe not the best, then it could run in seconds. In some case, good is good enough. How do you measure the efficiency of an algorithm? We could time how long it takes to run the code, but that would only tell us about that particular implementation in a certain programming language on a particular computer and just for the input it was given. Instead, computer scientists use a technique called asymptotic analysis, which allows algorithms to be compared independently of a particular programming language or hardware, so that we can conclusively say that yes, some algorithms are more efficient than others. Now, you can learn about algorithms and asymptotic analysis on Khan Academy.
Okay, so are you happy with the video? Was it okay? Right. Okay. So let's see some things. All right. So let's move on. Okay. So in summary, we could be able to say that if we have an input list, but first we have to have a problem to solve, right? Now, as I mentioned a while back, we should have an input and you should know your output. And in the middle, there's a process wherein you actually implement your algorithm, okay? Thereafter, after doing so, then that's the only time that you could be able to write some code, okay? I know you're always excited to write code. However, it's not good to be stuck just looking at the screen, not knowing what to do, right? So it's better that you think of the algorithm first before we actually start coding. Okay, so moving on, as what the videos actually showed, there are actually different ways to depict and write algorithms, okay? So if you'd like to show how an algorithm looks like, you could actually show it in terms of a pseudocode or in terms of a flowchart. Flowcharts are actually like what? Illustrations of boxes and ovals and all, and arrows, right? And you could be able to write this using the traditional pen and paper, or feel free to use any, what do you call this one? Any text editor of your choice so that you'd be able to type your ideas into it, right? Okay, says here, flowcharts are usually for long programs. Scratch, yeah, Scratch is actually like what? Jigsaw puzzling. There are like pieces that have commands in it already, right? And you start like what? Putting it together to create something, okay? So that's what Scratch is, all right? But that is already like, yeah, it's actually program logic formulation. It's trying to build up your your mindset into the logic of how programs work, which is actually pretty good. Anyone here worked with Scratch before? Yeah, okay, cool. How about the MIT App Inventor? Not yet. It's actually it looks like Scratch, however, it's actually into like what? Mobile, right? Okay, yeah, that's cool. All right, so limited? Yep, it's very limited. You couldn't be able to do anything or everything that you want because you're actually what? You're actually restricted on the available tiles that you could use, right? You couldn't be able to like fully embed what you'd like to put into. All right, so, okay, so everyone agrees. Cool. So let's continue. So as I mentioned a while back, right? How to depict it? Yeah, you could use a pseudocode, something like this, which actually contains the steps. You have your input, you have your output, then you have your process. Or if you don't want to show it this way, then you actually write it using what? A flowchart. Okay, so flowcharts, yeah, as I mentioned all back, you have an oval that actually shows the start and the end of an algorithm. This rectangular figure here actually shows you your I/O, your input and your output, right? This parallelogram here actually shows you a process, okay? I'm sorry, it's still I/O, sorry. And I'm sorry, yeah, it's a process, like printing and inputting something, and then that's it, okay? Simple. So this is the comp sci I have in mind. Yep. For starters, it definitely is. Getting thirsty. Okay. So these are just some definitions of the flowchart symbols. Okay. These are the basic ones. You'd be able to create what? Myriads of different solutions just by using these symbols. Okay. So of course, since it's a flow chart, then you have to indicate how it actually flows. Got it? It's not just a bidirectional line. It should be a what? A line that actually shows the next step that you're going to. Okay? And you could also have decisions. You could have loops, as what has been shown a while back. Programming is simple. There are only 3 constructs. You got sequential, you got conditional, and you got repetitive. That's it. Sequential is one instruction is actually being executed one after the other. So line 1, line 2, line 3, line 4, line 5, until end. That is sequential. Conditional is you have a certain statement is actually being executed depending on a certain condition. So if it's true, you do these statements. If it false, you actually do other statements. That is conditional. And the other one is, or the last one is repetitive. Repetitive indicates you actually need to repeat the same instructions over and over and over, depending on a certain condition. Got it? So it's pretty basic. Sequential, conditional, repetitive. That's what makes up what most of the programs that we have. Okay? So you could actually use, anything, everything, and depict it into a flowchart, whatever questions that comes into your mind. Let's say, for example, should I do my homework now? This is pretty much typical from our students, okay? Look at the algorithm and I guess you would agree, right? You have homework? No, you're lying. You always have homework, right? If it's yes, it's due in less than 12 hours? No, okay, so you do a lot of things. Procrastinate more. It's not yet less than 12 hours. And then, if it's less than 12 hours, okay, then you start working. Right? Don't worry. All the homeworks that we give, you could be able to finish it in less than 12 hours. So there's enough time for you to play. There's enough time for you to watch, whatever. But yeah, it's just for one class. What if you're actually enrolled in multiple classes? So time management is very important and crucial at this time, right? Got it? Okay. I could give more examples. How about this one, right? What to eat for lunch on a Sunday, for example. Got it? Or what? Should I say hi when I forget the person's name? So what I'm trying to show is that algorithms, flowcharts, pseudocodes are not just what? For programming purposes, okay? You could actually create algorithms and pseudocodes in your daily lives. Okay? How about this one? Should I listen to my mom? Okay, you could write an algorithm for that as well. Right? Or, did I pass the test? Got it? So, if not, she might not give any allowance. Yep, let's go previous. I guess that's the one you'd like to see. Okay, cool, right? At least you know your roles. Nice. So definitely that's just about it. Okay, so let's try doing some drills. Okay, so say for example, we have this. A very simple question. Add 10 and 20. So what are you supposed to do? Maybe this is what you'd like to do to solve the problem, right? Maybe you'd like to define, let's say, a variable. Okay, first, a word actually came out here, variable. What is a variable in our, that comes in, what is a variable if you think? Okay, a variable is actually an entity that is used to store data. Perfect, right? Someone said here, Theodore said, a package to hold data. So it's correct. A variable is actually an entity that is used to store data. Here, we're actually using sum to store the data. And in this case, we're gonna store the sum of 10 and 20. Initially, we initialize it to 0. Then we take two numbers as input, and then we add both of them and finally print the sum. Okay? So you could come up with something like this. Come up with a solution first, a general solution to solve this problem. Thereafter, you come up with the pseudocode. Okay? If you don't want to create the pseudocode and you say that, I work better if I'm drawing it. So you could actually, what? Create a flowchart to solve the problem. Nathaniel is actually showing us the solution here written in C. Okay, so it's cool. Lol, I forgot to do Python. No worries. You'll be having a refresher on Python starting next week. No C, please. Nah, you'll be using C and C++ in what class is it, Gus? Data structures class? Yep, in data structures. So you'd be learning a lot of different programming languages. You could ask your freshman leaders. On their first year, they actually learned 3. Python, Java, C++. You agree? Or more? Did you do JavaScript already?
No, sir. It's only 3. Oh,
Okay.
and Swift.
We did Swift, sir.
Basics of Swift. Okay, so 4 different programming languages. But for this batch, I guess they'll be having Project Hatchery starting next semester. That is for February. So they're not taking Project Hatchery this first semester. Okay, no worries. You actually have what? More than enough time to learn programming while you're actually enrolled. Okay? So, how about this one? Find the sum of 5 numbers. You could actually say, sir, I could like define 6 different variables. Num1, num2, num3, num4, num5, and then 1 variable to store the sum, right? That works. However, it's actually pretty slow, right? What if I tell you find the sum of 50 numbers? Then you have to define 51 different variables. Got it? 1,000. So definitely you actually need the help and use of a loop. Okay? You could even store it in an array. You could use random as you would say here. No problem. Right? But maybe you could just come up with something like this. Okay? This is just an example solution. Okay? There's not one solution to a given problem. Each one of you would come up with different ways of solving problems, and all of you would come up with the same answers. That's what makes the challenge for us lecturers to mark your programs, right? Because each one of you have their own different way of solving problems. You have your own signature, as we say it. That's why it's pretty obvious if you actually copied from someone, right? So, or you could actually be able to show something like this, right? The flow chart should still be okay. I thought we're holding different numbers then adding them to array. It's also possible, Hassan, no problem. You could actually be able to store all of the values in an array and then sum up all the items of the array and store it in a different variable. It's also possible, okay? This one, we're not saving anything into an array. We're just asking the user to input a value of n, and then we actually add it into sum. Got it? And then until we were able to input 5 different values, then we actually would store it into, print it eventually. Should you, what's it? By using a for loop, yeah, if it's an array, yep. Any loop would actually work. A while loop, a for loop, a do while loop, any type of loop as long as your condition is satisfied. And what is the condition? We have to let the user input 5 different numbers. So you input 5 different numbers. If it's more than that, then you already exit your loop and then you output the sum of those 5 numbers. Right? Cool? Understood? Yes. All right. Now, okay, you're picking up quite well. Okay, so how about this one? Yeah, actually, hello world 10 times. Pretty much similar to the previous one. Quite easy, right? This is actually easier compared to the previous one. Okay, Yeah, I should have made it like question 2 and then the last one is question 3. Okay? But understood? Yep. Printing is actually the standard. Okay. Can we move on? Yes. Right. So, these some important notes that you need to look into. Okay? There are many ways to solve a given problem. So there are also many ways to draw a flowchart and many ways to write pseudocode. There's not one solution to solve a problem. Although, right? Although there are some things that actually makes a certain algorithm stand out from the other, right? That is actually making your algorithms more efficient. Okay? There are multiple ways to solve a problem, and your first solution is not always the best or accurate solution. Okay? These are things that you need to look into and put into practice. Right? Okay. So, almost done with me talking, and then yay. Yes. Okay, Michael, anything? None? Okay, no problem. Right. So we're gonna look into sorting algorithms. Okay. Tomorrow we're gonna see each other again, right? And this time you will be the ones who are actually going to give us a discussion and not us giving a discussion. Okay. I'm not yet sure if we'd like you to work by groups, or maybe we could still assume that it would be better that you work independently. Gus, how do you want to do it? Should they do it as a group, or they do it individually first today, and then they meet, and then we create groups for them tomorrow, and then they should.
Do we still have time today?
No, not today. For today, it's just like, okay, we let them work on something on their own time. And then tomorrow we group them together so that they would be able to discuss their sorting algorithms with your friends, and they could be able to, and after that they discuss it with us.
Okay.
Okay, agree?
Sounds good.
Council will decide your fate tomorrow. What is this? Okay, no worries. Let me just look into, let's try defining what the sorting algorithm is first. Okay, so sorting algorithm says here, it's pretty much very useful. I mean, you actually would like to make or search for something very quickly. So the best way to do is actually to sort things and then use it, right? So it says here, there are many things in our life that we need to search for. Let's say a record in the database, roll numbers and merit, right? A telephone number, whatever, right? So it actually would be a mess if the data was kept unordered. So it's actually easier that to do a search, we have to sort it first, and then it's actually falls into place. We actually make it more efficient, right? Sorting says here arranges data in sequence, which makes searching easier. Now, there are a lot of sorting algorithms that are available already, and a lot of programmers actually try to implement it, and they use different types of sorting algorithms depending on the data that they're working on. Okay, some sorting algorithms are faster compared to the other algorithms. Some algorithms are more efficient compared to the other algorithms, right? So here we have some common sorting algorithms. You have bubble sort, insertion sort, selection sort, quick sort, merge sort, and heap sort. Okay, there are like 6 different algorithms. What are we expecting you to do? Okay, so this is what is expected. First, oops, sorry. Oops, no, sorry, not yet. I'm sorry, I haven't. I'm not going to show you what the is expected of you yet. Now, what makes algorithms stand out? It's efficiency. Okay, so we always have to make sure that we always speed is always of the issue, and of course space. Remember that your computer's memory is actually not unlimited. Got it? It's not limited. It's always limited, so there's always the issue of space. So, okay, this one's cool, right? You can run Doom on a pregnancy test. Cool. Okay, so so in order for us to be able to judge which algorithm is better, then you have to know the time it takes to sort the given data and the memory space required to do so. This is a course that you will learn in your more advanced computer science courses like data structures and analysis of algorithms. As early as now, the solutions that you submit, we actually don't care if it's very efficient or not, as long as it works. Got it? As long as it works, even if it's very, very, very slow, if it works, it's okay. Got it? On the first semester, you're forgiven. But come the second and third semesters, once you learn more about algorithms and data structures, then that's the time that we actually look into program efficiency, right? Let's make a brute force password hacking program. Okay, if it was brute force, it's gonna take forever, right? How many possible combinations are there in like, what, 10 characters? Okay, moving on. So, what is expected of you? You have to look into the different sorting algorithms that are listed here. Okay, there's bubble sort, insertion sort, selection sort, quick sort, merge sort, and heap sort. Okay, 6 different algorithms. What do you need to find out from these algorithms? Okay, let me show you an example. Okay, this is just an example, yeah. I mean, you could be able to search about these different algorithms on your own and discuss it with your friends tomorrow. However, just look into these things, which are quite essential. Okay, first, you look into the background and definition of the algorithm. Okay, find out what that algorithm is, how it came into life, for example, right? Just look into the background and definition. Thereafter, after looking into a background and definition of the sorting algorithm, you have to see how it is being implemented in pseudocode, okay? Or in plain English, right? This one, how it's written here, it's more of what? It's more of a pseudocode. Can't be C or something? Can, no problem. Can. But it would be better if it was in terms of a pseudocode or a flowchart. Okay? Yeah, seaweed notes, seaweed comments, that is. Okay? Because as early as now, we don't want you to be thinking about data types and those stuff, and syntax. Syntax is the least of your worries. Okay, why do I say syntax is the least of your worries? You have a compiler to do the task to check it for you. However, a compiler could not check semantic errors. Okay, semantic errors are logical errors. There's not one compiler or interpreter that could be able to catch semantic errors. So don't think about syntax yet. I agree with, what's his name? Nathaniel. Syntax is like the last thing you need. Okay? When do we do OOP? Semester 2, when you study Java. Right? So you come up with how it was implemented. Recursion is a programming style. Okay, so it's actually a function calling itself inside that function, right? But you have to make sure that when you design your programs to be recursive, it has to terminate at a certain condition. If not, then you're actually trapped in what? Oblivion. Loop. A loop is actually different. Okay. Loop actually uses constructs like while loop, for loop, do while loop. All of them are actually what? Repeating statements based on a certain condition. Okay. Recursion is calling the same function within that function. But the parameter that you're passing to it is actually different each and every time you call the function. And you just need to have a terminating condition to stop the recursive process. So recursion is like the infinite loop from scratch. No, it's not. Okay? Recursion is a programming style. It's not a programming construct. Got it? You could actually solve majority of the problems that are given to you without using recursion. But if you'd like to experiment and try out, no problem, it's still okay. Cool? Okay. Then, because yeah, I guess one of the sorting algorithms, let's see. Do we have quick sort in the list? Let me go back. Do I have quick sort in the list? Yep, I have quick sort. I have merge sort. Okay, this actually, you could actually come up with a solution using recursion. But you could still be able to implement it just by using loops. Okay? So, what is your task? Look at those different sorting algorithms, learn about the background and how it's defined. Look into how it was implemented using an algorithm or a pseudocode or a flowchart. Definition and history and pseudocode, yep. And of course, it would be nice to see a simple example or a simulation of how it actually works. Okay, so given the algorithm that you use, you have to try it out with an example data and then show how it actually works. Is shell sort in the list? I guess it's not, right? So it's okay. Let's just stick with the basics. Okay? Yep, just Google it. No worries. We don't expect you to, what? Imagine the different sorting algorithms. Okay? But yeah, try understanding how it works because yeah, you are going to discuss it with your friends and thereafter you're going to discuss it with us. Okay? And then, how are we gonna improve or optimize the said algorithm? Right? Because I mentioned a while back, right? The first solution is not always the best solution. So, maybe they already came up with a way to improve bubble sort. Okay, so let me show you how they actually improve bubble sort given this slide. There, they actually included a certain flag or variable that actually checks if I need to swap or not. Okay, so you have to do your research with the other, what do you call this one? Sorting algorithms as well. Cool? And I guess that's it for our talk for today. Any questions or clarifications?
Okay, done.
Sir Jude, would you please give your contacts at the end of the session? You have it already, right? We are in the group of Binusian 2024. Okay. All right. So that's how life works. Now, okay. You could contact us through our email, or, I mean, you have our numbers. We're in the same group in WhatsApp. So feel free to communicate and ask questions if ever. Right. So what are you supposed to do? You just go through the different algorithms, right? There are like 1, 2, 3, 4, 5 more: insertion, selection, quick sort, merge sort, and heap sort, right? And then look into the background and definition, the algorithm, and then in order for you to be able to clearly understand what the algorithm is showing, you use a test data to simulate how the algorithm works. Got it? Yes. Okay. Simulate. Notice that this is just like 2, 4, 6 different numbers. And then look into the possibility of how this algorithm could actually be improved, and then show another simulation of how they do it. And that's basically it. Okay? Is it cool? Is it okay? So some of you are actually, I guess, writing code already. And do we do this for all sorting algorithms shown before? Yep. Is it too much? Okay. Okay. So if it is too much, I suggest, okay, we have freshman leaders here. So would it be possible, do you have the list of all the students? Okay, so if it's too much, we could actually do something like this. You group them 5 groups. You put them in 5 groups, groups of 5. How many students are there? Yeah, 40? So each group should at least look into at least one algorithm la. Okay, just one algorithm should actually do. Is it possible? So if we have, how many students do we have? 40? Okay, let's say for example, we have 40 students. Okay, do you have the list? Anyone has the list? Freshman leaders? Okay, okay. So the freshman leaders have, okay, Nicholas, let's say for example, you have the list of students. Okay, you group them by 4. So if there were 40, at least 4 in each group. Okay, so 4 in each group, there will be like around 10 groups. Each group, at least, how many? 2, 4, 5. 2 algorithms each group. Okay, so 2 groups will actually be doing insertion and selection. Another 2 groups will be sorting quick and merge. Another 2 groups will be doing hip and, okay, maybe let's include bubble jugula as a bonus. Okay, I know it's not so easy to create groups now, but yeah, I'll be needing the help of our freshman leaders. Oh, wait, I see a familiar face here. Lelouch. Where are you, Lelouch? What's your real name, Lelouch? Are you Zero? Can't see his name. Okay, so you are Zero. So Hassan, you're Zero. Cool. Let's see the other avatars. Who's this guy? Okay. So there are a lot of Code Geass fans here. Right. So, any updates?
There's 38 students, sir.
Okay, 38. So it's okay we group them by 4, right? 4 students.
Yeah.
Okay. So once we have 4 students per group, then one group at least 2 different algorithms. So that yeah, you wouldn't be overburdened by looking into 6 different algorithms, just 2 per group. Would it be possible for you to assign it?
Hold on.
Okay.
So I think we can try and just group them with the with the assigned groups already.
Okay.
They have CS1, CS2, CS3, CS4.
Okay. Okay, that's good. Right. So let's say, for example, CS1 looks into yeah. But bubble sort has been discussed already, so we have to remove it from the list. So you have insertion, selection, quick, merge, and heap. Okay. So it's just like up to CS4.
It's up to CS9.
Okay, perfect then. Perfect. Okay. So it's like CS1, 2, 3, 4, 5, and then we go back again 6, 7, 8, 9. Right? Should be okay. So, do you agree? CS1 will do insertion, CS2 selection, CS3 quick sort, CS4 merge sort, CS5 heap sort. Then we go back to CS1. I'm sorry, CS6 insertion, CS7 selection, CS8 quick, and CS9 merge. Cool? That's, I guess, the best solution we could come up with right now, right? Okay, it's settled then. But so far, you wouldn't be working as a group yet, right? What I'd like you to do is you just try reading about that certain algorithm by yourself first, so that tomorrow you would be able to what? Clearly discuss with your group mates, right? The algorithm, at least everyone will actually have a little bit of knowledge about that type of algorithm, so the discussion would actually be more fruitful. Cool? Yep. Okay. Gus, we're okay with that, right?
Yeah, I think so. And hopefully tomorrow you guys can discuss, and then I don't know, maybe create some visualization maybe to show how it works maybe.
Yep. Simulation.
Yeah.
The simulation would be nice. I mean, I don't know how you're gonna do it, but yeah, it should be nice to see one. Okay? You could do role playing if you like. But yep. Okay. So make an actual call to confuse the new comp sci student. You're bad. Okay, so what time is it? 10:24. I guess it's okay for us to convene, right? Not unless you still have questions or need some clarifications. None? So we're cool? Yes. I mean, we can visualize in Minecraft. Yeah, okay, bisa. Any way you'd like to show the simulation would be okay. Okay, I see a lot of weebs here. Time to leave. Okay, so I guess, and I hope that you learned something today. We'll be seeing each other again tomorrow. And yeah, make wise use of your time. I guess you still have some other activities for you today, or after this class, it's done. Cool. Another 2, okay. Okay, have fun and enjoy your other classes then. See you tomorrow. Right? Okay. Bye.
Thank you, sir.
Bye, everyone.
Bye, guys.
I'll see you tomorrow.
Later.
Later.